It's a great pleasure to have Tom coming to Princeton, SOTOF, and he'll tell us about the holographic map as conditional expectations.
All right. Thank you, Nadi. So it's a pleasure to be back in Princeton via Zoom. So I'm going to tell you about a paper that I put out recently. And let me just tell you what the main takeaway is. So, by the way, interrupt me if there's some technical problems or if my iPad does something funny. So the main takeaway.
Can you speak up, please?
You want me to speak up? Okay.
Or get closer to the microphone.
Okay. I can just try to speak louder. Is that better?
Yeah, that's better. Maybe okay. Just my earring as I'm getting home, I don't hear well.
So the main takeaway is that some concrete statements. So the first statement is that quantum error correcting codes that have been used to model ADS-CFT naturally give rise to this object called the conditional expectation. And this is a well-studied mathematical structure in operator algebras. And so while this is sort of not really new, it's just an observation based on other people's work. It's useful because now you can go and look up all these results about conditional expectations in the math literature and see if they apply to ADS-CFT. So as one example of that, this perspective allows me to give sort of a strengthening connection to super selection sectors, which in quantum field theory. So this is a subject in algebraic quantum field theory. And there was a recent paper by Cassini, Huerta, Magan, and Pantelli who sort of made this point that there was some analogy between ADS-CFT, the holographic map in ADS-CFT, and super selection sectors. And it took me a long time to appreciate this paper, but now I see that this paper is very important. There's some, then I'll talk about some more speculative things. So I'll talk about multiple boundary regions when we think about restricting the algebra of the quantum field theory to multiple regions. And here we'll find some issues. So in particular, what I'm going to be studying here is something called exact recovery. So there's going to be no errors. I'm assuming sort of the recovery maps are error-free. And it's well known that this has shortcomings. And so I'll sort of make this clear. I'll give an example of this. The hope is this, what I'm doing here is just some initial study. This is my first pass at this problem. So the hope is that these shortcomings are not fatal, and some of this nice structure that is revealed here at least survives when you look at approximate error correction. And I'll continue with some more speculative ideas for studying entanglement wedge phase transitions, which have become important recently. All right, so let me start. I'm going to discuss a model of entanglement wedge reconstruction, which often goes under the name of complementary recovery. So this is sort of work that started with Ahmed and in the ADH paper, and then was more sort of formalized using results of JLMS in this Dong Harlow Wall paper, and then a paper by Harlow. And more recently, there was some work by Kang and Kolchmeyer who generalized this to sort of infinite dimensional Hilbert spaces, in particular to general von Neumann algebras. And so that's what I'm interested in. I'm interested in thinking about this problem with general von Neumann algebras, just because in the von Neumann algebras for local regions in quantum field theory are known to be of type 3. And so many of the results when you work in finite dimensions with finite Hilbert spaces just don't apply. So this was studied by Ken Koltmeyer, so let me sort of summarize the structure. And what I'm going to do is I'm going to put it in a slightly different language. I'm going to use the language of quantum channels to describe what's going on. Okay, so the starting point is the physical Hilbert space. So this is kappa. So this you should think of as just the boundary, the Hilbert space of the boundary conformal field theory. Okay. Then there's a code subspace, H, which is also a Hilbert space. You should think of that as the bulk gravitational theory, the Hilbert space that's sort of describing the bulk gravitational theory or the effective field theory in ADS. It's not entirely clear, at least to me, exactly how to define this. But I think sort of the spirit of this quantum error correcting approach to holography is that it shouldn't really matter. So maybe the details of exactly how you define this code subspace are not that important. But you should get, the physics of general relativity sort of as a low energy limit, no matter what you do in some sense. Okay, so then we have these two Hilbert spaces, and then we need some map between them. So I have this isometric embedding, V, which takes me between H and kappa. So it takes me between the bulk Hilbert space and the boundary Hilbert space. It's isometric, so V dagger V is 1 on the bulk Hilbert space, but VV dagger is a projector on the boundary Hilbert space. And so I'll call that projector E, and that just, you can think of that as just the code subspace projector. It's projecting to the code subspace in the boundary Hilbert space. And so the question of entanglement wedge reconstruction is basically how does this map, this V, this isometric embedding, how does it restrict to local algebras? So now I think about local algebras, subalgebras of all the possible algebras, operators on these two Hilbert spaces. And yes, and the question is, how does it restrict under that? So the standard picture I'll give is as follows. So here's a picture of ADS CFT, I guess ADS3 CFT2 on a t is equal to 0 time slice. We have some boundary regions, and associated to those boundary regions are algebras, are operator algebras. They're just sort of all the operators that you can think of in that region. They're bounded operators that act in that region. And so these are M and M prime. So M prime is the commutant, which I'll define in a little bit. But we also have in the bulk algebras, and they're somehow associated to the boundary algebras. So the bulk algebras in this case are N and N prime. And in particular, it's, with a lot of people's work, it has been realized that the algebra that you should associate in the bulk to the boundary algebra is found by looking at the Ru-Takinagi surface that computes the entanglement entropy in ADS CFT. So if I try to calculate the entanglement entropy of, say, the reduced density matrix associated to the boundary region M, then I would, look for some minimal surface that ends on the boundary of M, and I compute its area. But also, when you do that, there's a natural region in the bulk, which is the region between the RT surface and the boundary region. So this region here. And associated to that region is an operator algebra, just like on the boundary. And I'll call that N. Okay, so good. So now in reality, these are boundary algebras. I'm going to take them to be von Neumann algebras, and you should think of them as being sort of actually not associated to a time slice, but associated to a causal diamond. So a causally complete region in the boundary. So for example, this is a picture on the boundary. And in particular, it's a subalgebra. So M is a subalgebra of all possible bounded operators on kappa, on the boundary Hilbert space. And is associated to this bulk region, but also it should be some causally complete region in the bulk, and so that's often called the entanglement wedge. And I'm also going to assume that it's a von Neumann algebra and it's a subalgebra of the bulk operators. And of course, the commutants are clear. They're just all the operators in the respective Hilbert spaces that commute with those operators. So M prime, for example, is just all M in the bounded operators of kappa, which commute with M. So maybe I should have a prime. Good. So now, and similarly for N prime. Now, developments in the quantum information approach to ADS-CFT, in particular, starting with this Takasaki formula,
Tom,
which computes the entropy.
Yeah, sorry, Tom. Can I ask a quick question about your previous slide? I'm sorry for interrupting.
Yeah.
So you have the M and the M prime, they're commutants. So what about, again, operators that live exactly at the points between the two regions? So the way you've drawn it,
so
there's
operators
two regions
in the center.
Right, so
yeah,
what?
Like here, something here. Yeah. Yeah, they're just operators. They would be operators in the center.
So also the endpoints of your line, if I really go to the boundary,
yeah,
again,
here
the operators in the center. So they're part of both M and M prime.
Yeah. So yeah. For example, Z of M is M intersect M prime.
Right. Okay.
Now it's a very interesting question whether that. Sorry.
Wouldn't you also say that because they're infinitely localized, they don't belong to the algebra?
Yeah. Right. So that's what I was about to say. So essentially, it's an interesting question whether ZM exists, and in fact, there's theorems in algebraic quantum field theory which suggest for at least simple regions that ZM is trivial. There's another question about whether that's true in the bulk, and in the bulk, it is slightly different because it's gravity. So maybe the area operator at least is something that often people think of as living in the center. I'm not totally sure whether we should think of it that way, but yeah. But I will for this talk. I just this is an interesting question. Okay. So, but I should say that this method is powerful enough that I can have that. I can still have centers, and I can deal with that. So in some sense, if you're not really sure, you just keep it general, and then maybe you can try to prove it later. Okay. So developments in this quantum information approach to ADS-CFT, in the Takasaki formula, and then quantum corrections, and then this JLMS, which told us how to compute relative entropies in the bulk, which is very important, allowed for a precise characterization of how to relate N and M. So how are we going to relate N and M? And so what I'm going to use is a version of, well, it's actually it's derived from JLMS, but it's a much weaker condition than JLMS. So it's called the DHW condition. So this is a condition that's going to relate N and M. It's going to seem a little bit mysterious to begin with, but hopefully it will become clearer in a little bit. So the condition is as follows. If I take two vectors in the bulk Hilbert space, and I compute their linear functionals, I'll explain what that is in a little bit if you don't know, restricted to the commutants of N, so N prime, for the two different vectors. And if those are equal, if I consider all vectors psi1 and psi2 such that those are equal, then when I map through the boundary through this isometric embedding V, they should also give equal linear functionals on M prime. Okay. So this is a condition that relates N and M prime. And I'm going to give it a name, and I'll use this name a lot and it also won't be totally clear why I call it this, but it will in a little bit. So I'll say if this condition is true, N is reconstructible from M. Okay, so it's just the sort of simple condition on these commutants. Okay, so let me explain.
Is this a condition on what? On N?
It's a condition on
the pair N and M. What is it?
Yeah, it's a condition. It's a condition on the pair N and M. It's a condition on how N and M are related. So it says that for all, for all psi1 and I said it here, but for all psi1 and psi2 such that this is true, then this has to be true. Okay, that's the condition. Now. Yeah, so let me unpackage the notation a little bit. So omega psi is this linear functional. For vectors, it's simple. It's just the expectation value in psi. So it's often called the state in the algebraic quantum field theory language, and if you like, it's a version of the density matrix. In particular, omega psi is a global pure state on in the bulk Hilbert space. And this defines all correlation functions. So, but when I use this restriction symbol, I just mean instead of thinking about all possible operators on the boundary, I'm going to restrict to a subalgebra. So I'll restrict to n prime. And really, this is the algebraic version of reduced density matrix. So a reduced density matrix in the region n prime. Okay. Now, physically, what is this saying? So it's saying that two states that are the same on n prime could easily differ on n. In particular, in general, they're going to differ by unitary. So there's going to be some unitary on n, and these two vectors are different. But that difference cannot be detected in n prime. So it can't be detected in n prime. So it's sort of a version of privacy. So whatever you do in n can't be detected on m prime. It's often stated, this DHW condition is often stated in terms of relative entropy. It's basically that if the relative entropy between two vector states restricted to n prime vanishes, then the relative entropy on the boundary for m prime should vanish. So that's this statement. Of course, they're totally equivalent because if the relative entropy of two vector states vanish, then the linear functionals have to agree. And in particular, but the reason it's usually stated in these terms is it's derived from JLMS, which gives a relation between the bulk relative entropy and the boundary relative entropy, which is much more general than this because it allows the relative entropy to be different, to be non-zero. But that non-zero value is preserved through the holographic map. But here we're just looking at the value 0, so it's sort of a special case. It's a much weaker condition. The condition that we're going to use is believed, so based on JLMS and other works after that, it's believed to be correct up to non-perturbative errors in G Newton. Although more recently, there's some subtleties here. In particular, you should really only apply it to something called the reconstructible wedge, which is slightly different from the entanglement wedge. But it's not very different if your code subspace is sufficiently small. Or if you're, and you're not near an entanglement wedge phase transition. I'm going to assume exact. So we expect there to be errors, but I'm going to take it to be exact. Okay, and as I said, this is just the first pass at this problem. And I really want to study the non-exact version. It's just much harder. Okay, so good. So now we have this condition. The interesting thing is to apply this condition twice. And that's where the name complementary recovery comes from. So we say so I'm going to use the following language. I'm going to say that N is C reconstructible, where C stands for complementary from M if n is both reconstructible from M and n prime is reconstructible from M prime. Okay. All right, so that's just a definition. I'm going to come back to that in a little bit. But to get to understand these conditions, we need a theorem. Okay, and so this theorem turns out to be well, it's going to tell you why I say why I'm using this language n is reconstructible from n. So this theorem has a long history, it turns out. So it first appeared in ADS-CFT, I guess in DHW's work, and then more explicitly in Hollow's, in a paper by Hollow, and then more recently in the infinite dimensional setting in this paper. But it turns out that it actually, once you state it in terms of quantum channels, which I'm going to do, it goes back to an old paper in the early 80s, and actually even well before that. There's some papers in the 60s which talk about this kind of theorem. So it's sort of well known. So it's the following. It says that the following conditions are equivalent. So the first condition is the DHW condition that I was just talking about. Okay. The second condition is the following. So remember this isometric embedding V. We can use that to act on operators. So we were acting on states before, but now we're going to look at things in the Heisenberg picture. So in particular, I'll define this map alpha G, which is a global map between operators on the boundary Hilbert space and the bulk Hilbert space, and it's just defined by conjugating by V, V dagger V. Okay. But so that's just true. That's always true. But the condition, the DHW condition, is equivalent to what happens when I take alpha G and I restrict it to local algebras. So if I restrict alpha G to M prime, I'll call that alpha prime. Then the non-trivial statement is that alpha prime now sends operators in M prime to N prime. Okay, it need not have. In general, it's just going to send operators to here. But after you include this DHW condition, it actually sends it from M prime to N prime. So really, this is just the Heisenberg picture version of condition 1. So condition 1 is like the Schrödinger picture, and then condition 2 is like the Heisenberg picture. And so that's the second condition. That's the second statement. And then the third statement that is equivalent is the reconstruction statement. It says that given this map alpha prime, which sends M prime to N prime, there exists a special map on algebras, which as I'll explain it a little bit, is a quantum channel. Or what I think of as a quantum channel. So alpha prime, so there exists a map beta, which maps between N and M without the commutants. And this map is special. It's called a star homomorphism. It means that it preserves the algebra, so it satisfies this. And it satisfies the following condition, that when I act beta n on this isometric embedding V, I get Vn. Okay, so let me unpackage all of this and with some comments. So
sorry, I got lost. What is the role of item 3? I can't see the rest of the slide. So is this a condition and a theorem or a comment or?
Oh, 3? No,
I just got lost. I lost the logic here.
Yeah, sure. Let me explain.
You're stating the main theorem, so these are equivalent. Okay, thank you.
The following conditions are equivalent. Yeah. So DHW is equivalent to the existence of this beta. Okay. And so what I'm going to use throughout this is sort of this equivalence between, in particular, alpha prime and beta. So once you have alpha prime, then you have beta. And so that's what the theorem tells you. And so this correspondence between alpha prime and beta is sometimes in the paper that I referred to above is called the dual map. And really, it's actually sort of a version of the PETS map without the modular conjugation operators, if you know what that means. but I won't go into those details. These alpha prime and beta are quantum channels. So in the Heisenberg picture. So often, if the quantum information literature, quantum channels are in the Schrodinger picture. They act on states, on density matrices. But it's more convenient in the operator algebra language to talk about things in the Heisenberg picture, where they're maps. They're completely positive. They have some continuity requirements on operator algebras. Okay. And then finally, the last condition 3 explains why I use the word reconstructible. So the last condition just says that n is a bulk operator. N is a bulk operator. And beta of n is a representation of that bulk operator on the boundary Hilbert space. So that's the reconstruction map. That's exactly what we mean by entangled wedge reconstruction. And in particular, it acts in the right way on the code subspace. That's this last statement that's in square bracket. It's in the square here. Okay, so good. There's some technical things about this statement that I didn't sort of go into. This various maps have to be alpha prime is faithful, beta is unital. And these statements are not necessarily, but they make life a lot easier. And they follow, if you make an assumption about the kinds of states that you're looking at. In particular, you have to assume that there's just one cyclic and separating vector, V psi, for the algebra M. And the cyclic and separating just means that it's sort of a fully entangled state. So, if you had the reduced density matrix, if that made any sense, then it would have full rank and the complement region. But that makes life easier. Because this beta reconstruction map is a star homomorphism, it means that the image is a von Neumann subalgebra of M. So that's important for us. So beta of n is, I'll call n beta. I'll just define it that way. And it's a von Neumann subalgebra of M. Okay, in general, that's not true of the image of a quantum channel. But it is true of this special quantum channel. Okay, so to summarize, this theorem applies to one reconstruction statement, but complementary recovery has two reconstruction statements, right? So I get, I apply this theorem twice, and this is the picture that I get. I have my boundary algebras, M and M prime, this corresponding bulk algebras, N and N prime, and then there's maps between them. And so the first time I play the theorem is in green. I get this beta map and this alpha prime map, and they're sort of acting in the complement regions. But then I apply it again to the complement region, complement reconstructible statement, and I get alpha and beta prime. Okay, so I get these 4 quantum channels. And so this is the picture you get when you have this C reconstructible statement.
Excuse me, Tom.
Yeah.
I'm having a little bit of a problem reconciling what you're saying with one of the things I thought I understood at the very beginning of this discussion of error correcting codes.
Yes.
Namely that if you assumed the algebra was exact on the boundary and the bulk, you would get into a contradiction, and saying that it only worked on the code subspace was important. And somehow you're saying that's no longer true. I'm probably not understanding.
Where did I say that the algebra wasn't exact? I'm taking the bulk and the boundary algebras to be exact algebras. That's sort of my input.
Yeah, but in some of the earliest papers on error correcting codes, there was a puzzle that error correcting codes resolved, namely that if I naively take an algebra in the center of the bulk, it seems to commute with everything on the boundary, and that's impossible. And this was resolved by saying that well, this wasn't really an algebra isomorphism. It was only true on the code subspace. So
so I think you're sort of going along the right path here. So indeed, I'll come back to the assumption of exact recovery. So one way to fix the problem. So one way to fix the problem that you're one way to state the problem that you're reminding us of is essentially that you preserve the fact that these are exact algebras, but you just say that they don't act exactly as expected. So there's some error. So I think that's sort of a choice. And so indeed, this exact assumption will come back to haunt us, and it will in exactly the same way as this, the ADH paper originally pointed out. But yeah, I mean, as I said, this is a first pass, and and yeah, I mean, I'll come back to non-exact recovery later. But yeah, I mean, this is sort of important, and yeah.
Thank you.
Yeah, but just sort of go along with it for now, okay? And yeah, okay. Good. So now, so you should think of this C reconstructible statement. When I say that, you should think of the entanglement wedge. So that's what that defines N as the entanglement wedge, and then there's some complement entanglement wedge as well. And so it's a strong condition. It's a very strong condition. If I go back to this just without the C statement, so just reconstructible, it's a much weaker statement. So in particular, it's true of any subalgebra. So if I take N, which is C reconstructible, any N twiddle, which is a subalgebra, is reconstructible without the C statement. Actually, we'll show later that it's an if and only if statement. Another way to see that it's quite weak is that if I have two algebras that are reconstructible, if I take the, if I take all operators generated by NA and NB, which is defined as this symbol here, this algebraic union symbol, then this is still reconstructible. However, this N, the blue N, which is C reconstructible, is unique if it exists. Okay, so the claim is when we have this entanglement wedge or this C reconstructible region, then there's a conditional expectation. Okay, so that's the first sort of new claim. And so I'll explain what a conditional expectation is, but just to cut to the chase, in this case, it's just a composition of two of these quantum channels, beta and alpha. So in particular, you see beta alpha works consistently if we go back to this picture here. So beta maps you from N to M, and then alpha maps you back, sorry, it's beta alpha. So firstly, alpha maps you from M to N, and then beta maps you back from N to M. And so notice to define this object, I needed both the green and the red statement. So I needed to apply this recovery condition twice because I'm using alpha and beta where neither have a prime on them. Okay, so the claim is that this is a faithful conditional expectation. It's a map between M and its subalgebra N beta, this quantity N beta. So that's, and it importantly preserves the code subspace. Okay, so that's the claim. Let me explain what a conditional expectation is. So as I said, a conditional expectation is a map between two operator algebras, in particular between an operator algebra and its subalgebra. So B in this case is the subalgebra of A that satisfies the following condition. So if I apply E to B2A, B1, where B is in the subalgebra, then I can just sort of pull out the factors of B2 and B1. This is called the bimodule property. It's sort of a somewhat rare object. Its existence is non-trivial for general von Neumann algebras. If you're working in finite dimensions, it sort of always exists, but when you're working with more non-trivial von Neumann algebras, it's not always guaranteed to exist. Its name comes from probability theory. It's a non-commutative, really non-commutative version of conditioning on some random variable b. And then there's just some really simple examples. So the simplest example is in finite dimensions, which is essentially a partial trace. So if I have a Hilbert space HA, and then I have, it factorizes into B and C, and then I trace over C, then that's something in particular, if I take the partial trace on operators, then that's something that takes an operator in A, or bounded operators on the Hilbert space A, to bounded operators on the Hilbert space HB, which is a subalgebra. And you need to normalize it. So there's this normalization condition, normalization fact here. Another example is just if you have some symmetry, and you just average over that symmetry using the Haar measure, then that takes you from an algebra to a subalgebra, which is just the subalgebra, which is the fixed point algebra of that symmetry. Okay. So these are two examples. I'm not going to really say what the relevant one is in ADS-CFT. It's, from tensor network pictures, it seems like this is a relevant one, but it doesn't really matter. It's going to come out of this DHW condition. So that's, I'm just going to study it as something that arises. Okay, so let me come back to the claim. So I claimed that there's this conditional expectation. So let's just check a few conditions about it. So firstly, an important thing that maybe I didn't emphasize is that a conditional expectation fixes the subalgebra. So in particular, if I apply E to the subalgebra B, I just get back B. Okay, so let's just check that that's true here. Well, the subalgebra, remember, was this beta of n. But E I defined as beta alpha beta. It's quite easy to show that alpha beta is the identity using this reconstruction map. Okay, so alpha beta sort of cancels, and then you just get beta back. And in a similar way, you can check that. So that doesn't. You can also check this bimodule property, but I won't go through that. Similarly, you can check that E fixes the code subspace. So if I feed into it states from the code subspace, V psi, and I apply E, then I get back V psi. And that just follows from the following manipulations. E is just beta alpha again, but V is alpha itself. So you again get something like alpha beta alpha, and you can cancel the alpha beta, and you just left with alpha, which is the original. Okay. All right, so that's sort of a simple set of calculations. But it has powerful consequences. In particular, there are many things that were derived from in these original papers, which are sort of now trivial, or trivial once you look up the right paper. So for example, this JLMS condition, this quality of relative entropy through the code, is something discussed in various papers by Petz and others. There's also this equality of the bulk and boundary modular flow, which I'm not going to, these two things I'm not going to go into details for, but in fact that's well known from a very old paper by Takasaki, who studied conditional expectations and showed that indeed the modular flow in between the subalgebra and the algebra are sort of mapped to each other. There's an equality between them. And so good. So these are some consequences. I'm going to go through another consequence in a little bit. Let me give you a somewhat misleading picture of what's going on. Okay, so we have these boundary algebras M. You should think of them as quantum field theory algebras. And so a classic example is just Rindler space. So if I think about Rindler space on the boundary, then there's some algebra associated to that. And I'll call that M. But now we know that there's these subalgebras n beta. And so I'm going to draw a picture of these subalgebras, which sort of looks like a sharp subalgebra here. In reality, it's not really sharp. It's just some subset of operators in M. And it's, in fact, it shouldn't be sharp. If it's sharp like this is some sort of, say, quantum field theory subalgebra, then you can show that there's no conditional expectation between these two. It's impossible to write one down. This is a somewhat misleading picture, but I'm going to draw, it's easier to draw pictures like this. Okay, but I also had this complement region, M prime, and there's a similar story on the complement. So then there's this N prime beta, and so there's some subalgebra on the left as well. Now, one thing you can show is that if I take this subalgebra on the left and I compute its commutant, then this is some algebra in pictures here, which is sort of this region here. It turns out you can show that there's another way to write this commutant. It's just all of the operators generated by the original algebra M and one operator E, where E is this code subspace projector VV dagger. So you can show that. That's interesting because it's actually something called the Jones extension. It plays an important role in index theory for subfactors. So this is a subject which is quite mysterious to me, but apparently it's where the Jones polynomial was first introduced. So we're studying particular operator algebras, type 2 von Neumann algebras and their subfactors. This Jones extension plays a very important role in sort of constraining this quantity called the index, which is something which measures roughly sort of, how many times n beta fits in M. So there's some subalgebra, and so you can sort of think of how it fits into M to quantify that. Okay, so M1 is this Jones extension, but interestingly, it arises from this complementary recovery map. So it's the complement of this region. Yeah, so this is an example of what I wanted to point out, which is, now that we have a name for this object, it's a conditional expectation. You can go ahead and look up all of these earlier papers that studied them and see whether they're relevant for ADS CFT. Okay, another object that's going to play a role in the next section is something called the relative commutant. So if I have this subalgebra n beta, then the relative commutant is defined as this intersection. It's just the intersection between all operators in M and that commute with n beta. So if you like, it's this sort of region in here, in this sort of fake picture that I'm drawing. And I'll call that NC. Okay, so now I've introduced this relative commutant. It turns out that you can derive the so-called Ru-Takenagi formula that arises in these error-correcting codes that were sort of emphasized by Harlow. Naturally associated to this conditional expectation, there's a theorem by Takasaki which says that the operator algebra M essentially factorizes. And it factorizes between this relative commutant and the subalgebra. So it factorizes a tensor product between NC and N beta. This is not quite true in general, but it's essentially, it's almost true in general. So for general von Neumann algebras, it's almost true. It requires factors and some property called normalcy. But actually, there's a version of this which doesn't require any of that. And having a tensor product like this is not trivial for von Neumann algebras. Okay, but not only that, the states fixed by the conditional expectation, as Takasaki showed, that they are always factorized. So they have a factorized form. There's some state restricted to the relative commutant, tensor product with some state restricted to the subalgebra. And so, just by this factorization property, we know the entropy that we might be interested in for the boundary region M is just the sum of the two entropies, one on the relative commutant and one on the subalgebra. So this piece on the right is going to be the bulk entropy. The bulk entropy, and then the thing on the relative commutant, as you might guess, is going to be the area term. So this is like a generalized entropy. There's a bulk entropy and plus the area. And so how do we see that that's an area term? Well, the relative commutant term here. Well, let's think about the state on the relative commutant. But rho we know is fixed by the conditional expectation, so I can just put in an E here. But E of NC takes a very particular form. So E always maps to the subalgebra. So E of NC is in N beta. But then I can do the following. I can take any operator in the subalgebra N beta. I can use the bimodule property to push it inside. It commutes with NC because the relative commutant is M intersect N beta prime. So it commutes with N beta. So I can push it over here, but then I can use the bimodule property to pull it out. So the end result is that you see that E commutes with N beta as well. So it's in N beta and it commutes with N beta. That means it's in the center. And so we learned that rho of NC can be evaluated using this fact that E of NC is just in the center. So I can write it as a sum over these central projectors if I don't assume the center is trivial, times some numbers. And these numbers, well, they take as input NC. So if I get a number and I take as an input an operator, that's just a state, right? That's the definition of a linear functional or a state. So in particular, these are just states on the relative commutant.
Sorry, are you assuming these are one-dimensional projectors?
Yeah. So yes. These are minimal projectors. Yeah. Minimal. So I'm assuming something about the relative commutant in that it's type 1 or something.
I mean, is that a reasonable assumption?
I don't know. I would love to know. I think that understanding whether that's true in ADS-CFT, yes. I think that would be an important statement that you might be able to get some traction on. I think it's probably true.
Can I ask a question?
Yes.
Yeah, so the equation you write down relating the entropy, I mean, in the case you're talking about, I mean, if it comes from local quantum field theory, both sides are infinities, right?
Yeah, correct. Yeah, so I'll make a comment on that in a little bit. So yes.
Yeah, I mean, but the way it's only interesting when the algebras involve the finite dimensional ones in your case. But otherwise,
I wouldn't say that's the only interesting case. I mean, you can, the following setup applies to the Sommerfeld double setting where I actually expect everything is type 1 algebras. I want to be a little bit more general, and I'll make a comment about the type 3 case, which I think is maybe interesting. I'm not sure, but I will make a comment about it. So for now, I'm assuming type 1, but yeah, some of these statements don't assume type 1, although anytime I talk about an entropy, I assume type 1.
Well, in the case of type 1, the existence of a conditional expectation is automatic.
Right.
So
that's fine. Yeah, that's fine. But maybe not one that fixes the code subspace. So that's the important thing there. Yeah.
Okay.
So all right. So at the end of the day, you can write this formula for SM as just this sum over the expectation value of these central projectors times the entropy of these states gamma. But these states gamma are just associated to the conditional expectation. They don't depend on the state that we're interested in. They just depend on E. So at the end of the day, you write this as just the expectation value of some operator which lives in the center, which I'll call Ln. It's a sum over these central projectors times this entropy plus a bulk entropy term. And so this is the generalized entropy formula. And it sort of comes out naturally from this conditional expectation. Okay, so this is exactly, this is the RT formula that was discussed by Harlow. And so as I said, really this is only for type 1 because I'm assuming the entropies are finite. I think it's sort of interesting that in the type 3 setting, I can't define entropies, but I can still define this area operator. And I think that maybe that's an important statement. But yeah, I think that's somewhat interesting. Yeah. Okay, so still assuming finite, going back to assuming finite entropies, I'm going to write the following minimization formula, which I think looks a little bit like the Rutakinagi formula. So you can always prove that Sm of some state on the code subspace is always less than or equal to a sum of two entropies, where the entropies are going to be associated to some region N, which is reconstructible, not necessarily C reconstructible, just reconstructible. So any reconstructible algebra, I can compute the bulk entropy for that algebra, and I can define some term which looks a little bit like the area term. I'll call it the area term, and I'll come back to whether you should think of it as such. But it's basically the state on the relative commutant. Okay, and so you can prove this formula, and you can also prove that equality is achieved if and only if there exists an algebra N which is C reconstructible from M. Okay. So I think this is suggestive. Looks a little bit like the Rutakinagi sort of minimization, and in particular, it sort of has quantum corrections in it. But there's some issues with this analogy. So firstly, here's one issue. Not all subalgebras of the entanglement wedge, I would have thought, it's true that not all subalgebras of the entanglement wedge have a generalized entropy, or what we should really think of as the generalized entropy, as having a larger generalized entropy. In particular, if I look along the entanglement wedge horizon, if I just shoot sort of null rays out from the RT surface, then SGen actually has to decrease by quantum focusing. So there's some issue with that here in this approach. The area operator isn't really an operator. It was just some entropy. It's not in general an operator. There's a way to fix that by assuming the conditional expectation is related to something called the minimal conditional expectation, and then it's fine. And the third problem is the following, which is if the statement is actually that if you achieve the minimum for one state that is cyclic and separating for some algebra, then it turns out we achieve it for all in the code subspace. And so this is also not something you really expect from Rutakinagi, but I know that this, as a fact, this is just a consequence of exact recovery. So in this exact approach, I'll never be able to fix that problem. Okay. All right. So that's the structure so far. Let me see how far I can push it. So I'm going to think about multiple boundary algebras, M1 and M2. And the first thing I'd like to prove is entanglement wedge nesting, which is kind of an important property of ADS-CFT regions, entanglement wedges. So I'll prove the following statement. So it's that if N1 is reconstructible from M1, and notice that I didn't include C reconstructible here, I just said reconstructible, and N2 prime is reconstructible from M2 prime, and if M1 is contained in M2, then the theorem shows that N1 has to be contained in N2. Okay, so let's unpackage this a little bit. M1 being contained in M2 is a statement of causality. It means that M1 should commute with M2 prime. So if I draw my boundary regions, I'm going to draw M1 here, and I'm going to draw M2 prime over here, and they're sort of causally separated. Then in the bulk, I have some entanglement wedge regions at E1 and E2 prime, which I'm drawing here, and then the algebras that I'm thinking about are subalgebras. That's the claim, at least. And so this theorem shows that N1 is contained in N2, which then implies that N1 commutes with N2 prime, which means that the bulk regions, any bulk region containing the entanglement wedge has to be causally separated. So that means the entanglement wedges also have to be causally separated. So that means that the bulk regions nest if the boundary regions nest. Okay, so that's entanglement wedge nesting. This theorem also proves this statement, this if and only if statement that I mentioned in the beginning. If I take M1 to be equal to M2, then you can see that it proves the if and only if statement. Good. Okay, so
sorry,
the next thing
could you go back a little bit and I
yeah.
have a question.
Yeah.
So this statement that E1 and E2 are C-reconstructible, what were E1 and E2? And is this a consequence of the previous statement or?
Yeah, so this is just to guide you. E1 and E2 are not a subject of the theorem. So it's really just N1 and N2 that are subject of the theorem. And it just says that if N1 is reconstructible from M1 and N2 prime is reconstructible from M2 prime, then the bulk algebras should commute, okay? Which seems totally reasonable. But what I'm saying here is that if I took, so if for example, I took N1 to be E1 to be the sequent reconstructible region, and I set M1 to be M2, then this theorem proves that any reconstructible region on the left has to be contained in the left entanglement wedge. So it proves the statement that I was making before. But yeah, so in this theorem you could put C reconstructible and that's totally fine, and that directly proves nesting. But this proves slightly more. Okay, if I remove the C statement here. Okay. Is that somewhat clear?
So let's see. So E1 is what is C reconstructible. That's the definition of E1.
Yeah. E1 is C reconstructible.
So it's something smaller than the previous N1.
No, it's something bigger than the previous N1. So N1 is always contained in E1. So yeah, I mean, if you like to avoid confusion here, which apparently it was a little confusing, consider E1 in this statement and E2 prime in this statement, which are C reconstructible regions. Then this is the region I'm talking about. This is the region I'm talking about. And it's just telling me that those two regions don't overlap like this. This doesn't happen. Okay. That's all this theorem is saying in that case.
Okay. Thank you.
So the other thing I want to explain is the consistency of this conditional expectation. So if I have a subalgebra M1 on the boundary is a subalgebra of M2, and they're both C reconstructible with some bulk algebras N1, N2. We know from the previous theorem that N1 should be contained in N2, but we also can show that the conditional expectation associated to M2 restricts consistently. If I restrict it to the subalgebra, then I get E1, the conditional expectation associated to M1, and that's a non-trivial statement. So actually, this consistency proves that this exact complementary recovery structure, if you apply it to sort of multiple boundary regions in this way, is the same as some mathematical structure that was introduced by Longo and Rehren to study superselection sectors. So this is some mathematical generalization of superselection sectors, which is a way of sort of studying global symmetries in algebraic quantum field theory. But this was a generalization of that structure, and it's interesting to me that this arose here. And this connection was pointed out in this paper, and I think I'm just sort of showing my contribution to this is basically to show that this quantum error correcting approach in the exact case gives you exactly the same structure as a super selection sector. Okay. So the next thing I want to discuss is issues. Okay, so there's some issues with this approach, and this comes back to Tom's question. So consider the following setup. So if M2 and M1 are two boundary regions that overlap, and they overlap in some non-trivial region, then you can prove the following theorem. If N1 is C reconstructible from Ni is C reconstructible from Mi, where I is 1 and 2. And there exists a vector psi in the bulk such that V psi is cyclic and separating for this intersection region. Okay, so that means that the state in the intersection region is sufficiently entangled. Then you can show that N12 is C reconstructible from M12. That is, the bulk entanglement wedge associated to the union of the two boundary regions is just the union of the bulk regions. Okay, so this is sometimes called additivity. It's the bulk algebras are additive with respect to the boundary algebras. And it's not what we expect from ADS CFT. So we know that if we have two boundary regions that overlap, we take their union, then the bulk region should be much larger than the union of the bulk regions. Right? So it should include this sort of region here. So this was sorry, I didn't mention, but this was an issue that was pointed out a while ago by Kelly. And this just sort of formalizes it in a theorem. It uses in an essential way this cyclic and separating property, which I'm not explaining too carefully in lieu of time. But the solution is clear. It's essentially is not to give up on the cyclic and separating property, which turns out to be a completely reasonable assumption. The vacuum for these boundary algebras is cyclic and separating, and we expect the vacuum to be in the code subspace. So it's totally reasonable. The solution is to give up on this exact recovery. Then we have approximate recovery, and then cyclicity actually loses its power. So it's harder to prove things, and in particular, you won't be able to prove this. So this is the classic example in the ADH paper where there's some algebra here, some operator in this region that you can't reconstruct unless you have the union of the two. So in fact, non-exact error correction is important to get that sort of basic example that was pointed out. That's just to come back to Tom's question.
What is the degree of non-exactness? So what is is there a notion of how accurate it is?
I'm not sure. I would guess that the error, yeah. So good. So there's a natural question, which is, let's say it's very close to exact. Can we still use cyclicity? And actually, it's super hard to do that. I tried. It's not easy. I'm not sure. But I would guess that it's still, non-perturbatively correct. So there's just exponentially small errors that lead to this. So I think that's kind of interesting to understand exactly how that happens.
So the idea is that there is some parameter like n or the central charge theory, and it's in that parameter that things are going to be exact.
Right, exponentially in that parameter. Yeah, I think so.
Mm-hmm. Maybe this is the same question as Juan's, but what is the definition of approximate recovery?
Good question. Yeah, I don't know. So for example, you might ask, you might ask for
I'm expecting you to formalize it in terms of, the alpha and beta and using some norm condition.
Something like that.
Okay.
This is a natural thing. I don't think this is quite right, but this is might be something that you guess. So that's a condition. Where epsilon is, supposedly exponentially small. So you would, it's nice to have these maps still, but you might assume that they don't work very well, or exactly. Okay, So
I have a question. So
yeah.
even though the error that you introduce is exponentially small, it's designed to solve a problem which appears perturbatively in the bulk, right? I mean, this like the problem of the three regions and so on is some
seemingly,
situation.
Yeah, that's right. I don't have much to say except that this cyclicity thing. If you try to prove, try to prove an approximate version of this using cyclicity, then you very quickly go from the error to log of the error, for example. That can happen.
Okay, very good.
So it's not beyond that. I somehow don't think that's the right approach, but that can happen. So yeah, I mean, I think this is a really interesting open question to understand. So, better. Okay, so I'm going to continue. I'm going to ignore these issues and just keep going. And at some point I'll stop. But, well, maybe I should stop now. How much time do I have?
So strictly speaking, you are at the end.
Yeah.
Since there were some questions, you can keep going for a while.
Okay, so maybe I can have 2 minutes and then I'll finish.
Even more.
Okay. Well, I won't talk for too much, but I'll just say something about this. So it would be silly of me not to try to understand an entanglement wedge phase transition, which is an interesting feature of holographic these entanglement wedges in ADS CFT. So so imagine you have two boundary algebras, M1 and M2, that are disjoint. Then it's known that the entanglement wedge in the bulk undergoes a phase transition as you sort of deform the geometry of the boundary regions. So if the boundary regions are very small to begin with, then the entanglement wedge is just the union of these two. Sorry. The union of these two bulk regions. But if they become too large, then the entanglement wedge becomes connected through the bulk. And so I'm drawing pictures in a two-dimensional CFT. This is a phase transition that happens as a function of the cross ratio of the endpoints of the intervals in vacuum, and the phase transition happens when x is equal to 1/2. And I'm just focusing on the 2D case, essentially because the complement of two intervals is still two intervals. So that's sort of useful for me. So I'm going to assume continue to assume exact complementary recovery. So I have N1 is C reconstructible from M1 and so forth. But then the question is, there's some bulk region N12, which is C reconstructible from M1 union M2, from the union of the two boundary regions. The question is, what should I pick for N12? And so holography suggests that there's two options. Either N12 should be locally generated. It's additive by N1 and N2. That's the picture on the left here. Or the complement region should be additive. So the complement region is the complement of the two intervals, which is now generated by M3 and M4, these boundary regions here. And then they have bulk regions associated to them. And if I take the union of those two and I take the commutant of that, then that's this blue region in the bulk, which is the non-trivial entanglement wedge. So those are the two options. So I gave this name, a code where this is true, a name. It's dual additive. So either it's additive for 1, 2, or in the complement region. I think likely, if you were to show that something like this happens, it's a consequence of a CFT having the usual story, having an extended Cardi regime, which is a well-known feature of holographic CFTs that requires large C and a gap in the spectrum of primaries. given this structure, it's natural to ask what controls which algebra to use. Again, you can use this quantum minimality condition that I wrote down. In particular, you can write a formula for the entropy, again, assuming type 1 for simplicity, as just the minimization of two bulk entropies, which look like two generalized entropies. In particular, the area operators here are just the area operators for these four regions, 1, 2, 3, 4. And you can show that they add like this, assuming something called the split property. Yeah, so, okay, let me skip that comment. I tried to study this code in a sort of a novel way, I thought, which was to introduce, so assuming this structure is true, one thing you can do is you can introduce a new code subspace, and you can, which turns out to be exactly orthogonal to the previous code subspace. In particular, you use the split property to introduce this code subspace, but I'm not going to go into details on how you do this. But the end result is that on this new code subspace, you have a different reconstructible algebra to the old code subspace. So in particular, you can find a situation where the bulk algebra N1, 2 is additive on 1 and 2 in this new code subspace, but in the old code subspace, it was additive on the complement. Now, I sort of think of this as some kind of analog of what happens in a Hawking page phase transition, where you sort of, if you think of that in sort of a state language, where if you think about sort of the thermal ADS as being some kind of pure state in 2 copies of ADS, and then as you increase the temperature, you get the Hawking page phase transition, where you get sort of a black hole, a maximally extended black hole, and these 2 code subspaces are, roughly speaking, the 2 code subspaces that you would get by thinking about small perturbations around those 2 solutions. Now, it's known that in reality, those 2 code subspaces are not orthogonal. There's small, exponentially small G-Newton overlap between those 2 code subspaces. And I think, the fact that in this exact approach you find something which is exactly orthogonal is sort of indicative of this of this feature of exact recovery. So in particular, I think we need to go beyond exact recovery to see small non-zero overlaps, and that will solve many of these other problems. Okay, so let me finish. I've sort of made it clear that the obvious thing to do next is to go beyond this and study exact recovery. There's a lot of interesting things that happen there. There's this alphabet story, this breakdown of complementary recovery, including this very interesting recent paper by Jeff and Chris, which, the structure of which would be nice to see in this sort of algebraic language. Okay, so let me finish there.
Are there any more immediate questions?
Yeah, I have a question, if it's okay. Suppose that I took a lattice quantum field theory at its critical point, but on a finite circle or finite sphere, and I started trying to apply all of this technology. A lot of the theorems that were difficult to prove are simple there because everything's finite dimensional. I just wondered whether there's anything that you've kind of assumed here that wouldn't work in that case. I mean, suppose I have a lattice quantum field theory at its critical point, and I make a tensor network construction of the theory in the way that Evenly and Vidal did. And so I've got a sort of discrete version of ADS space inside my lattice quantum field theory. How much of this would, some of it would be easy because everything's finite dimensional, but would it all be true in that case?
I'm a little confused. At the critical point, isn't everything infinite dimension?
No. I'm taking the continuum critical point. Okay. Of the lattice theory, and I'm putting the lattice theory in a finite volume. Okay. So everything is finite. Okay. It's just that there are very large fluctuations that are cut off by the volume. So this is.
Aren't there also UV fluctuations that are? So I would have guessed that in that case the local algebras are type 3 and.
No. It's a lattice theory. The local algebras are type 1.
But if I take the continuum limit,
you're not taking the continuum limit.
I'm not taking the continuum.
You're just taking the coupling to its critical point on a finite lattice with finite volume.
Mm-hmm.
So I could study everything that you've done in that context, and I'm just wondering whether there's some easy way to check if all of the things you're saying about exact recovery are true or not true, and the extent to which they're true.
Well, I mean, I guess that model doesn't have a holographic dual. I think there might be some subalgebras.
This can be if you have a proper lattice version of n equals 4 Yang-Mills theory, which we could argue about how hard it is to do that. But if you did have it, it would be very, very close to something that has a holographic dual. Okay.
Yeah, I think you're sort of just getting at the UV issue, right? Whether that's important or not. I mean, in some sense, you might just say, who cares? I put it on a lattice, there's some cutoff, and I'll work with that. And indeed, that's usually how you define entanglement, and it's fine. And I'm not saying that that's bad. And in fact, that's a great approach. And the tensor networks that people have written down, I think, sort of fit into that in some sense. But I kind of like this language that you get from this operator algebra, even if it's even if you just end up applying it in such a setting, it makes things sort of nice. So yeah, I don't know. I mean. I think it sort of also sort of tells you the kinds of things that you can do and you can't do, the things that you expect to survive the continuum limit, things that are finite instead of UV infinite, and so I think that's also nice.
So what I'm sort of getting at is that I think that these paradoxes about exact recovery would be there even in this system.
Oh yes, yeah, no, for sure, yes. Yeah, I agree.
Okay.
Yeah, no. In fact, they were sort of, they've been discussed. These paradoxes have been discussed before. I'm just putting them in this new language. So yeah. Mm-hmm. They're still there.
Can I ask one more question?
Yes.
Okay. So I like this operator algebraic approach, but you see. If we're really concerning about quantum field theory, then as you said before, is type 3 saturation, right? So in that case, the relative entropy, I think, plays more fundamental role. So I'm just curious if there is a formulation of this RT prescription and this holography, but in the relative entropy language, because that's completely independent of cutoff.
Yeah, there is. So there's this JLMS formula, which tells you how to relate the bulk entropy and the boundary entropy, relative entropies. But sort of, in some sense, you drop the area term. And the area term is quite interesting. It's not like it's not interesting. So I think that there are ways to regulate that even in the continuum limit. So one thing you can do, which I've worked on in the past, is you can introduce this thing that we call the reflected entropy, which is just the entropy of this type 1 splitting factor that you naturally get. And so you can always replace, if you have type 3 boundary algebras, with some, even in the continuum, there's some natural regularization which gives you a type type 3, and then there's natural regularization that gives you this type 1. And so I think it's still interesting to think about that question, because the entropy, the regulated entropy, has this area term. This area term is in ADS-CFT has this n squared in it, right? And where that comes from and why that arises is interesting, and yeah, it's important to understand in this language.
Oh, I see. So what you're saying is that in the case if you use reflecting entropy, then the error term will show up?
It should, yeah. I mean, another way to do it is this mutual information regulator for ratio. So you can compute the mutual information for two very close regions, which should exist by the split property. And that will give you also an n squared. And where that comes from,
what's that? Sorry, n squared. What do you mean? The large n? You mean
yeah, large n or whatever. Yeah, depending.
Okay,
I mean,
I see.
Yeah.
Okay. All right. Thank you.
Sorry, can I ask a question? One thing you said, which was that you proved that for any two states in the code subspace, you had the same reconstructible algebra.
Any two states, yeah, that's right. Yeah.
Yeah. And you said this was clearly a consequence of exact error correction. Can you explain why?
Well, it's actually, again, related to the cyclic and separating property. It's sort of, once you have it for one state that's sufficiently entangled, what you can do is you can use the reconstruction itself, which is this beta map. You can use it to prove that it's true in all states.
I see.
It's just because the reconstruction is this very powerful homomorphism. So you can star homomorphism. So you can sort of act with multiple operators and you get all the other states. Yeah. But if you have some error, then you won't be able to do that.
I see. Okay. Thank you.
Well, if there are no more questions, then maybe we should thank Tom for a wonderful talk. Thank you.
Thank you.